Hello, welcome. Today let's try to solve another Leetcode problem, 111, minimum depth of a binary tree. So what's the meaning? We have to find the leaf node. So for example, this is the root. We must find the leaf we must find the leaf node of the tree. So for example, this 9 is a leaf node, and this 15 and 7 are also leaf node. But what is the minimum depth? It is the level 1, this is the level 2, so the minimum depth is 2. So what is the conditions? The condition for the leaf node is if the left node does not exist and the right node does not exist. Yeah, both of them meet the conditions. So we're gonna return the depth for this node. For example, yeah, when it comes to 9, so the depth is 2. When it comes to 15, the depth is 3. When it comes to 7, the depth is 3. So we can use the BFS with a queue to solve the problem, because BFS is also like the shortest path, because from this node to here, this is the shortest path. When we find it, we're going to return immediately. Yeah. So the condition is if the left node not exist and the right node not exist. So we're gonna return the final answer. And we are sure this is the shortest because we are using BFS. Yeah. You can also use a DFS, but DFS will be a little bit difficult. Yeah, because you need to check all the conditions. The conditions is root not exist, left not exist, but right exist. So the right not exist, but left exist. So the right and left both not exist. So there are too many conditions. You have to check its conditions and find it. But for BFS, you only need to check one condition. So that is the left and the right not exist. Both of them not exist. You find the answer immediately. And first of all, you also need to check the root node. Yeah. Now let me implement the BFS. So if not root, so this means the root node does not exist. So we're gonna return a 0 immediately. Then we can prepare for the BFS. So we can prepare a deque. Inside the deque, it would be a tuple. It would be the root node. So this means the root node exists. If the root node exists, we're gonna prepare a depth. So the depth should be 1. Because for the root node, if it exists, the depth should be at least 1. Yeah, let me make the typo right. It should be depth. Now I'm going to check this queue and pop it out. So the node and depth should equal to q.pop left. So I pop out the root and the depth. Then I'm going to check the node if the node exists. Yeah. So for the first step, this root node must exist because I've already checked. But I will put some left and right inside the queue. Sometimes this left can be none. Yeah, because I will use the next line. You will understand clearly why. Yeah, you can also write some other node, some other code. It's the same. So I'm gonna check this node must exist. Yeah, because if it exists, I'm gonna check the left and right if I would to append some node inside the queue. So I'm going to check if the left node not exist and the right node not exist. So I can use a not dot right. So this means, for example, we only have a node 3. The left and the right both not exist. Yeah, if I find this leaf node, yeah, this means I find a leaf node. So I gonna return immediately. So I gonna return the depth. Yeah. Otherwise, it's the situations like this. We have 9 and 20. So what we should do, we're gonna append. But here I can use extend, because here for this extend, it can be a none. If the left is a none, maybe, and the right I have a node. Yeah. So I can use extend. So code dot extend, and inside it will be tuples, node dot left and depth plus 1. And another tuple is node dot right and depth plus 1. So this is actually the entire code. Yeah, because I used this extend, so this means maybe I gonna append some none inside the queue. Yeah, but at least there is a node should be not none. Maybe both of them. So actually there are three conditions. So one condition is left node is not none, right node is not none. This is one condition. Another condition is left node is not none, but right node is none. Yeah, and the third situation is left node is not none. It's nine, but right node is none. Yeah, so I would prepare all the three combinations inside the queue, and after that, I will pop the node to check. If the node exists, I'm gonna check next. So for example, it is a nine. Yeah, and this nine left and right both not exist. So I'm gonna return the depth. It is a two. Yeah, let me first run it to check if it works. Let me check. Yeah, I still made this typo. I remembered I corrected it, but still, the depth. Yeah, so here it is 1 because it's the root node. I made some typo. I believe I changed this 1 to a depth. Yeah, as you can see, it works. Now let me submit it to check if it passed all the testing cases. By the way, the time complexity is ON, and the space complexity is also ON because this binary tree can be linear. And also we used this queue. Yeah. As you can see, it passed and it's pretty fast. So here we can also change this lines of code to check the conditions. Yeah. So we can change this line to if not dot left, we're gonna use append. So q dot append, and inside it's gonna be, let me append a tuple. Yeah, inside it will be this one. And similarly, I can check if not dot right. Let me copy this line. So q dot append inside this one should be not dot right. Yeah, we can also write like this, but this will be more lines of code. Now let me just run it and check if it works. Yeah, this may be easier to understand. Now let me submit it to check if it works. Yeah, as you can see, it also works. But the only difference is here, we put the node inside the queue. This node can never be none because we've already checked. Yeah, as you can see here, for the first node from the root, it must be not none. Yeah, because we already checked the root. If it is none, we're gonna return 0. If it is not none, this means the first node is not none. And then we're gonna inside to check. If both not none, if both none left and right, we're gonna return the depth. Otherwise, we're gonna check. This means we put this node inside and the node dot right inside. Both of them will be not none. So we don't need this line of code even, because the node will always be exist when we are checking like this. Yeah. Now let's just prove it should be okay. Now let me run it to check if it works. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, so this lines of code is just for, we don't need to check the node because we are sure the node always exists. So maybe this lines of code is more clear to apply the function of BFS. Thank you for